Okay, we're now going to begin Unit 7, and this is the first tutorial in Lesson 7.1. We are talking about chemical equilibrium. Chemical equilibrium is defined as the state when a reaction and its reverse reaction proceed at the same rate. So you want to write down this definition. When a reaction and its reverse reaction proceed at the same rate. Another way to say this is opposing reactions proceed at the same rate. You watch the TED-Ed video of the people's arms unattaching and going on to people's noses, and when the forward reaction equaled the reverse reaction, the system was at equilibrium. So let us consider a system where we have some dinitrogen tetroxide, and it is decomposing into two nitrogen dioxide molecules. This is the forward reaction, going this way. At the same time, once there are some nitrogen dioxide molecules, they are combining to reform dinitrogen tetroxide. That is the reverse reaction. We have a forward reaction and a reverse reaction. So, oops, I want to squeeze this whole thing in. As our forward reaction approaches equilibrium, its rate is, oopsies, slowing down. We learned last unit rate is fast as at the beginning. And as the reverse reaction approaches equilibrium, its rate is increasing. Initially, there's none of this, no nitrogen dioxide, so once there is some, then it can start recombining. So its rate increases. When they reach equilibrium, the rates of the forward and the reverse reaction are the same. The forward and reverse reaction at equilibrium are proceeding at the same rate. This graph is a graph of concentration versus time. Once equilibrium is achieved, the amount of the reactants in the products remains constant. It doesn't change. Although some of this may be decomposing into nitrogen dioxide and this may be reforming, they're doing so at equal rates so that the amount of each does not change. That happens once you reach equilibrium. When we show a system at equilibrium, we use the double arrow. This is a pretty poor double arrow. I'm going to redraw it. The double arrow tells us, because not every system is at equilibrium. As the video you watched earlier said, you can't unexplode something. But many reactions are at equilibrium, meaning their forward and reverse reaction rates are the same. This arrow tells you the reaction is moving this way. This arrow tells you some of this is recombining to make that. So a double arrow tells you a system is at equilibrium. Now we're going to define something called the equilibrium constant. In order to do that, we're going to think about the forward reaction. So here we have the forward reaction, same as N2O4 decomposing into two NO2s. If we were to write the rate law of this elementary step, it would be rate equals K forward times the concentration of N2O4. Now if we think about the reverse reaction, for this system at equilibrium is 2NO2 going to N2O4. Here it is written as 2NO2 going to combining to make N2O4. The rate law for this elementary step, assuming this is an elementary step, is rate equals K reverse times NO2 squared to the second order, because there's two of them. Now, since we just said a few slides ago that at equilibrium the forward rate, rate F for rate forward, equals the reverse rate, rate R, this is an R, we can substitute in our rate expressions, our rate laws. The forward rate law was K forward times the concentration of N2O4. That is equal to K reverse times NO2 squared. If we divide both sides by K reverse and by N2O4, Then the K's cancel, and this K reverses cancel, and the N2O4s cancel, and we end up with this expression. K forward over K reverse equals NO2 to the second order, or second exponent, over the concentration of N2O4. And this will become our equilibrium constant expression. The ratio of these are two numbers. The ratio of these rate constants are constant at a temperature, so as long as the temperature doesn't change, this is constant, and we call then this divided by this our equilibrium constant, and it is equal to the products, or NO2 squared over N2O4. So this is the equilibrium constant for the reaction N2O4 at equilibrium with 2NO2. So to generalize how to write an equilibrium constant for a system, look at this system. The little letters are coefficients. The larger letters represent molecules or atoms. And if we wanted to write the equilibrium constant for this forward and reverse reaction, this is a reverse one down here, we would take each product and raise it to the power of its coefficient. So the concentration of C raised to little c, the concentration of D, these brackets mean molarity, raised to little d, the power of little d, that's its coefficient, and divide that by the concentration of one reactant raised to its coefficient power, multiplied by the concentration of the second reactant raised to the power of its coefficient. So this formula, taking the products to the power of their coefficients, divided by the reactants raised to the power of their coefficients, is how you write the equilibrium constant expression. This whole thing is an equilibrium constant expression. So you can write down this as the and this reaction as the definition of the equilibrium constant expression. The value of an equilibrium constant is calculated when you have a real reaction and you put in actual concentrations and coefficients into this system. Okay, let us practice writing equilibrium expressions, which we call Kc. Little c stands for concentration, for these reactions. So for the first one, Kc will be equal to, we'll take our product, which is O2, right here, and raise it to the power of its coefficient. So it'll be raised to the third power. That will be divided by any reactants, and here our reactants are O3, and that will be raised to its coefficient, which is the second power. So that's for letter A. For letter B, our equilibrium constant expression is equal to our products. We only have one, it's NOCl. Concentration of that, whatever it is, raised to the second power, because its coefficient is 2, divided by the reactants. So we have NO raised to the second power, because 2 is its coefficient, and Cl2 raised to the first power, because its coefficient is 1. The third one, we're looking at this reaction. Our equilibrium constant expression, our equilibrium constant is going to be equal to our product, which is AgNH32 plus, this is a complex ion, so the concentration of Ag, parentheses, NH3, close parentheses, 2 plus 1, close brackets for the concentration. The coefficient here is 1, there's nothing in front of that, so no power over here, it's the first power, divided by our reactants, concentration of our silver ion, which is to the first power, multiplied by the concentration of our ammonium ion, NH3, our ammonia, not ammonium ion, ammonia, and that is raised to the second power because the coefficient of ammonia is 2. So those are 3 equilibrium constant expressions for these 3 reactions. Now, pause the video and see if you can identify the correct equilibrium constant expression for this reaction. Okay? Okay, let's see how you did. The products are SO3, the concentration of SO3 to the second power, over the reactants, SO2 to the second power, times O2 to the first power, making C the correct answer. You see, we do not put the coefficients in front here. If there's a coefficient in the reaction, it becomes a power in the expression. 2 more practice problems. You can pause the video and try them and then check. For the first one, Kc is going to be equal to your concentration of your product to the second power, because this is a 2, divided by the concentration of H2, your first reactant, to the first power, times I2, also to the first power. For the second reaction, our equilibrium constant is going to be equal to the concentration of our product to the first power, because there's no coefficient, divided by our first reactant, cadmium ion to the first power, times a bromide ion to the fourth power, because we have a 4 as a coefficient here. So this whole thing is the equilibrium constant expression for this reaction. And this whole thing is the equilibrium constant expression for this reaction. That is the end of tutorial 7.1. See you in 7.1b when we'll talk more about equilibrium constants.